Hey, welcome back, everyone. This explainer is brought to you by Forge College. So you can go ahead and completely put away those Solana CLI manuals from our last lesson, because today we are dusting off our Ethereum engineering hard hats. Seriously, I hope you're ready, because we are getting really hands-on with some core cryptography today.
We're continuing our journey through the Ethereum fundamentals trek, specifically focusing on the life cycle of an Ethereum transaction. Now, today's module is all about initiating those transactions. But wait, before we broadcast literally anything to the whole world, we need to know how to securely authorize an instruction before it ever even touches the network. So we're going to learn exactly how to sign transactions completely offline. Okay, let's just quickly glance at today's blueprint. We've got 5 parts. 1. Anatomy of a signature. 2. 4 steps to sign. 3. EIP 155 replay protection. 4. Scaffold your script. And 5. Safety first. Let's get into it. Section 1. Anatomy of a signature. Unsigned versus signed. So let's start with a really clinical, methodical dissection of our transaction, looking at it both before and after it gets signed. Think of it like inspecting your raw materials before they get permanently fused together. Notice how the raw, unsigned materials transform into the final serialized product? They do this by appending this sort of mathematical magic trick, specifically the V, R, and S components. Look at the core fields there, your nonce, gas limits, the to address, the value, and the data. Those stay exactly the same. But when we move from unsigned to signed, we aren't just saying, hey, I approve this. We are cryptographically binding our identity to these exact, unchanged fields. And I mean exact. If even a single decimal point in the value field changes, the entire signature just becomes totally invalid. Notice how the serialization changes too. We use RLP, that's recursive linked prefix, to encode the fields. On the unsigned side, it's just the core fields. But once signed, the RLP encoding wraps around those core fields plus those brand new V, R, and S signature values. Moving right along to section 2, 4 steps to sign the assembly line. All right, so stepping out onto the main factory floor, think of this whole process as our conveyor belt. First, we gather our raw field materials, picking our nonce, setting our gas, choosing our destination. Second, we crush all of that into an RLP signing payload. Third, we literally stamp that payload with our private key. And fourth, we assemble the final product, injecting that signature right back into the transaction data so the network can eventually read it. Let's actually look a bit closer at the machinery doing the heavy lifting in steps 2 and 3. So step 2 relies really heavily on Keycheck 256. Honestly, think of Keycheck 256 like a massive industrial crusher. See, elliptic curve cryptography can't just sign a huge, variable length list of transaction data directly. It just doesn't work. It needs a predictable, fixed size input. So Keycheck 256 steps in, takes our neatly RLP-encoded payload, and just compresses it down into a uniform 32-byte hash. This hash is the exact, unalterable representation of your transaction's intent, fully prepped and ready so your private key can actually do the signing. Then we have the ECDSA algorithm, specifically using the SEC256K1 curve, which acts as the actual stamp on our assembly line. It takes that crushed KEK at 256 hash and your highly sensitive private key, and it just mathematically merges them together. It outputs the raw signature scalars, which we know as R and S, and these are beautiful, highly deterministic hex strings that securely bind your identity to the transaction fields, all without ever revealing your private key. It's brilliant. Oh, and it also spits out a tiny piece of data called a recovery ID, which, actually, keep that in mind, because it's going to be incredibly important in just a second. Which brings us to section 3, EIP 155, replay protection, the bouncer. Okay, so we have R and S from our ECDSA stamp, but what about V? Well, that brings us right to EIP 155. The really crucial point here is that this solves a massive historical vulnerability in the network. See, in the early days, a signed transaction was valid on literally any Ethereum-compatible network. That meant if you signed a transaction to send test funds on a testnet, well, someone could theoretically copy those exact signature bytes, take them over, and replay them on the mainnet, completely draining your actual funds. Wild, right? EIP 155 fixes this by baking the specific chain ID directly into the signing payload. It basically acts like a club bouncer, ensuring a transaction meant for the Ropsten testnet club doesn't try to sneak its way into the mainnet club. But how exactly does it bake that in? It does it through that V component. The chain ID modifies the payload and gets encoded directly into V using this exact, quite simple mathematical formula. V equals the recovery ID, remember I said that would be important, plus 35, plus the chain ID multiplied by 2. It's just an elegant little piece of arithmetic, and by calculating V this exact way, the resulting number simultaneously tells the network how to recover your public key from the signature and explicitly states which specific blockchain this transaction is actually allowed to exist on. And boom, that completes our signature triplet of V, R, and S. All right, Section 4. Scaffold your script. Vibe coding task. Now it's time to take off the hard hat and put on those developer goggles. You are going to instruct an AI assistant to build a local offline script. The absolute secret sauce here is to force the AI to use low-level libraries, things like RLP and SCP-256K1. Because if you let it use high-level libraries like ethers.js, it'll just hide all the underlying magic from you in a single line of code. And we don't want that. We want to see the bytes. So you'll ask for specific functions to build the payload and sign the hash, and most importantly, like absolutely crucial, strictly tell it not to include any broadcasting code. We want to generate this signature entirely in a local air-gapped vacuum. So here is how you can actually build your prompt. Seriously, you can literally copy the exact text we've outlined to generate a totally plug-and-play scaffold. This prompt basically forces the AI to output a script that proves you can manipulate these raw hex bytes all by yourself. And the coolest part? When you run the script it generates, you'll actually see the Ketchak hash, you'll see the R and S values, and you will see the calculated V value print out right there in your terminal. It just completely demystifies the entire process. Finally, Section 5. Safety first, broadcast later. Hold your horses, though. Before we even think about touching the live network, we absolutely must run our final quality assurance checks. First and foremost, you must protect your private key. Never ever use a private key that holds real actual funds for local script testing. Just generate a fetch-burner key. Next, make sure your script actually prints the payload hash and those R, S, and V components out so you can visually verify them. But here is the absolute ultimate test. The gold standard of offline signing is step 4. You must always verify offline that the public address recovered mathematically from your fresh signature perfectly matches your expected sender address. If those addresses match up perfectly, it means your private key successfully bound itself to the transaction fields, the math is totally flawless, and the network is going to accept it. Which brings up one crucial final question. If a bad actor somehow intercepted this offline payload, could they alter it? Well, the answer is a resounding no. Any tiny change instantly invalidates the entire signature. You now hold a mathematically bulletproof, perfectly serialized text string right in your hands. Which means, in our next lesson, we're finally going to submit it to the network and watch the Ethereum nodes actually accept our instructions. To learn more about this and to continue your journey through other Web3 topics, make sure you visit forge.college. This explainer was brought to you by Forge College. Thank you so much for learning with me today, and I'll see you in the next one.